Good evening, everybody. Jai Bhim. I hope you're all uh, well and healthy, and all your loved ones are healthy in this very difficult time. Um, Today, I'm going to present a one-off lecture. It's really just to, uh, so we're off schedule. Normally, we have lectures on Monday and Q&A sessions on Friday, but because of a canceled lecture, I thought I would spend the time and just run through just an interesting special topic. It does relate to data science, of course, but you can view this lecture as just an independent lecture on a topic that is very much on everybody's minds. And what I would like to do, what the intention of this lecture is to give you some insight into the science behind epidemiology and modeling this current pandemic. And so, if since in the live lecture there's very few of us, I do encourage, if something is unclear, to please stop me, interrupt, and ask questions. I'm very happy to have a conversation and try and explain things as I go through them. So we are in the midst of in India, we're in the midst of a second wave. In other countries, they're actually in the midst of a third or a fourth wave, or even a plateau. And every country is very different. Every society is very different. Some are more similar to each other than others. But when we want to understand something as basic as how a virus spreads in a population, we really have to be mindful of the fact that there's a difference between understanding something and predicting something. So if we just think about the weather, okay, only very recently have we progressed to a point where our weather predictions can be trusted to, let's say, up to 3 or 4 days into the future. Previously, of course, it depends on the weather itself. There are some times when the weather is more volatile, it's more changeable than other times. But previously, it used to be that weather was hardly reliable more than 1 or 2 days in advance. And the reason isn't because we've understood, the improvement isn't because we've understood the physics really of weather better. The physics has always been the same for the last 150, 200 years. The difference is that in our modeling, we can input more accurate data. And so one of the most famous examples, I like to use, maybe not famous, but one of the most relevant examples I like to use is when people ask me all the time, why does India have a space program? How can a country where so many poor people, how can it afford a space program? Well, my answer to them is twofold. India is a lot of people, and its space program today has a budget certainly in US dollar terms is about 2 billion US dollars. I think that's about, it's 2 billion US dollars. It's a figure I pulled off of Wikipedia. And so with 1.4 billion of us, if you took that $2 billion and spent it on every Indian citizen, it would at most give them, a strip of ibuprofen. It's peanuts. It's nothing. It's very cheap for us. But one of the more drastic benefits to our citizens from our space program is the fact that India has one of the few civilian-led space programs in the world. Almost everywhere else, it has a very strong military component. This is true of China. This is true of America. I think Japan, India, and Europe are the few independent space agencies that have really a civilian-led space program. And in 1990, this is or was it 1989? I think it was 1990, maybe 1991. There was a big cyclone that hit Odisha, and 10,000 people died. Okay, and this is a humongous tragedy. Okay, and I think this is something that we should reflect on as Indian citizens, that this no longer happens. Okay, we no longer live in a country where 10,000 people die because of a cyclone. Um, of course, many more people are dying now because of a pandemic, but just focusing on this example of this cyclone, the reason people don't die anymore is because we have so much better weather forecasting. And this is because of our space program, because we have satellites, meteorological satellites, that are now so accurate in their data collection that they can feed information to the authorities, and they can plot the trajectory of the cyclone with such accuracy that they can evacuate people in time. And now, a few years ago, there was another cyclone of equal strength, maybe even more than the horrible cyclone that hit Odisha in 1990, around then. And certainly, the number of deaths, although every death is tragic, was in less than 10. So we've saved. So the question to why does India have a space program is what is how can you afford it, is what is the cost of 10,000 lives, and I think it's priceless. Okay, and so um, the reason I bring up this example is because just because you understand something perfectly well doesn't mean you can necessarily predict things with it. Because in order to make predictions, you need to have extremely accurate data to feed into your models. And what is a model? A model is a cartoon. It's a caricature. It's a cartoon. It's an approximation to reality that exists in a separate mathematical universe, either on a page, in equations, or in a computer model. And this model is only useful if it accurately describes this reality. And so, just as our improvement in weather forecasting has not come from a better understanding of the physics of weather, we've always known this. Nothing has changed it for the last at least 50 years, probably more. What has improved is our ability to make more accurate forecasts with our models. And so, what today's lecture will focus on is modeling pandemics, and all of the problems that are associated with maybe making predictions from modeling a pandemic. What I would like to emphasize is that there are lots of moving parts, but as is often the case, in a lot of science, a very simple model actually captures quite a lot of the broad features that you end up seeing. And so epidemiology is really the subject of trying to understand how diseases spread in a population. And we are going to go through the science of it. It's actually very simple. I hope it's something that everybody will be able to just sort of think through themselves. And this lecture is meant to provide an introduction to this modeling and the different types of models. And what I hope to do is to demystify some of the numbers you may have been hearing in the news, such as reproduction number, this R number, if you've come across it, and mitigation strategies to try and reduce the spread of the epidemic. So the concepts of R effective, which we will explain, and the concept of a herd immunity, which is something you may have also heard in the news. And so we would like to present, from the ground floor up, one of the most, if you like, the typical examples of studying epidemics, which is the so-called SIR model. Okay, we will derive it from scratch, I hope, in a way that is understandable. And from this simple model, I hope to present to you the dynamics of epidemics, how epidemics, run through a population, and how there are certain very, very predictable features of epidemics, and how there's very predictable effects you can do to lessen the blow of an epidemic via various mitigation strategies. After we understand this SIR model, I will then point out well, then I'll maybe even ask you why this model, what you think is not being captured by this model. And I will discuss also more complicated models, so-called agent-based models, and also consider network epidemiology. All of these things have fancy names, but underlying them is just plain common sense with some mathematics added on top of it. And um, none of this matters unless we can do something useful with it. And the useful thing we'd like to do with it is to sort of understand where we are over the course of an epidemic and what's coming next. And so this is the forecasting. And unfortunately, for something like a pandemic, there are so many local variables that are so different in so many different circumstances that this is very, very difficult. So we're very often left with having to make decisions based on incomplete information. So there's a lot of philosophical things that come up in all of this. Although this is a talk about mathematical modeling and some of the science behind it, there's actually some philosophical aspects. The word actually is in philosophy is called epistemology, which is the study of knowledge itself and the boundaries of knowledge. And one of the big epistemological questions that exists for pandemic modelers is, how do we make sense of what we're trying to understand and predict based on incomplete information? And this is not something we have a definite answer to. We have answers, but none is conclusive. And so I invite you to, part of this is an invitation to also allow you to have the tool of skepticism to, approach some of the information that you may be seeing in the news. And so let's begin. And everything begins in these sorts of discussions with this now cliched quote. Cliche means, it's happens so many times that it's so commonplace. And there's this quote by the statistician named George Box. And the statement is that all models are wrong, but some are useful. Okay? So what is meant by that is that models are not reality. Models are just some depiction of reality that one hopes is accurate for the purposes of the questions that we are trying to address. And so there are some models that are extremely useful, such as the laws of nature that we have, that you learn in physics class. These are some of the most accurate models of reality that we have. In fact, they're so accurate that there are some numbers in nature that we can calculate to 9 decimal places, okay? And then you go and you do an experiment and you find that it agrees to 9 decimal places. And then in the 10th and 11th decimal place, there's some error in the observation, so you can't be so sure. And so there's always going to be an experimental error. There's always going to be a theoretical error because you can't calculate everything to arbitrary accuracy. And so there's some numbers that we know. Some numbers are so spectacularly accurate that it's like, to give you a context of a number that's accurate to 1 part in a billionth, it would be like shooting a gun to the moon, and hitting a 1 paisa, a 1 rupee coin. Okay, that's how accurate they are. So some models are very, very useful, but some models are less useful. But all models are wrong. And this is even true in a fundamental sense for our understanding of nature. Because physics, all of our laws that we have, all of the rules we have for, let's say, understanding genetics, for chemistry, for physics, these are all approximate rules that work almost every time we check, in some cases. But it's not the final story. There's a deeper underlying reality that we've just got an approximation to. And in fact, what's happening underneath may be more complicated. And so our model is going to be wrong at some point eventually. So with that in mind, I just want to emphasize that modeling reality is an art. Okay, the manipulations of models for the logical consequences is what we call science. But the choice you make to model reality a particular way, this is a bit of a combination of an art form. Of course, it can follow a particular method, such as the scientific method. But if you ask a philosopher what is the scientific method, and it's actually very hard to come up with an unambiguous, 100% clean answer. Everybody who's a scientist thinks they know what it means, but there are subtle differences that make it actually fuzzy. So one of the main things that happens in all modeling is the art of ignoring things. We have to simplify things because reality is just much too complicated. And so we have to ask ourselves, what is essential for the phenomenon under study? So if I'm interested in something like, firing a cannonball off a cliff, okay, and so a cannonball has, a color, it has a temperature, it has a size, but when I'm firing a cannonball at a very high speed off a cliff, none of those things matter, really. Size, okay, maybe air resistance makes a difference depending how big the cannonball is, but to first approximation, let's say we're neglecting air resistance, it doesn't matter. So we can ignore these details. And in fact, it turns out that the motion of projectiles is determined only by the initial velocity. That's it. And the angle with which we fire it off at. You could have fired a cannonball, you could have fired, a marble, you could have fired God forbid, a human being, but all of these things would end up landing the same distance away, at least the center of gravity of this object. So, and this is for very well understood reasons that follow from Newton's laws. But when you want to understand projectile motion on the Earth, there are many things that you can ignore, and it doesn't help. I mean, a blue cannonball will end up having the same trajectory as a red cannonball. So these are details that don't matter. And the question is, what are the details that matter and don't matter when we're trying to understand how a disease spreads in a population? So we have to, before we do anything, we have to guess. We have to sort of step back and ask ourselves, what is essential? So we're beginning from the ground floor. We are about to go through the same logic that epidemiologists did at the very beginning before their field even had a name. Okay, so and the idea is, clearly you need a population in the first place, some population, and in that population there must be some subpopulation, or that subpopulation could be the entire population that can be infected. Okay, so this is the set of it's called the set of susceptible individuals. So it's not always the case that everybody in a population can be infected by a certain disease. Some diseases only affect affect children. Some diseases only affect people with a certain condition. So the susceptible population is some fraction of the population. If we're talking about something, I don't know, like the flu, some people have already had the flu, let's say last year, and so in a given year, some fraction of the population will have immunity to that flu. So they are not in the susceptible population, but some people are susceptible. Alternatively, you could have a vaccine for some diseases, and so some people who are vaccinated against that disease are not susceptible, but those who are not vaccinated are susceptible. Okay, so within the susceptible subpopulation, there is a disease, and it can spread via some form of contact, okay, with infected individuals. So once you have the disease, once you've caught the disease, what do? You end up passing it on to other people, okay? So you have the disease for some period of time, and then over that time, you pass on that disease to some number of people. Let's call that number R0, on average, okay? And then after that individual has recovered, they are now no longer susceptible, they are immune. Let's say that the disease, once you've had it, gives you immunity. So then they are removed from the susceptible population. The reason there are asterisks on both of these statements is that realize that these are approximations. These are simplifications that we're making for the time being. In this very simple case, we imagine a disease. Let's come up with some disease. Let's call it COVID, where initially there's some fraction of the population that's susceptible. In the case of COVID, it's everybody at the beginning in 2020. Nobody had it before. And then it spreads via some contact, either through aerosol transmission or through, contact of bodily fluids. And on average, there's some number. And this number, by the way, this R0 is a bit of a mysterious number, right? I mean, how can you predict how many people you're going to come into contact with? But let's just work in the approximation that everybody that gets the disease on average gives it to R0 number of other people. Let's say 3, let's say 4. We don't know that number exactly, but we have a good guess. And then once you've recovered from COVID, or if the case may be you've passed away from COVID, unfortunately, you are clearly no longer going to be infected again. And so you're removed from the susceptible population. So this is a first guess as to how we might think about modeling an epidemic. Okay. So this model, susceptible, infected, removed. Okay. And so removed could be either recovered or deceased, is known as the SIR model. And this, if you like, is the most elementary model in epidemiology. It is the equivalent of, if you like, the hydrogen atom in chemistry, or the simple harmonic oscillator in physics, or it's just really it's just the most basic, simplest thing you could think of. But when you have something so simple, it loses perhaps a bit of applicability to real life situations. Maybe it's a little too simple to model real life, but its advantage is that it becomes very easy to see the dynamics of what's going on. It gives you it makes it very, very clear what's happening, so that if you want to make a more complicated model, you are able to separate the different moving parts and understand separately what the different elements of the dynamics are. And although one can and should consider more detailed models, the SIR model more or less captures the basic trends of an epidemic. And I've spoken to various epidemiologists. I actually have a side interest that I'll get to towards the end of the talk. It's directly related to my research on epidemics on networks, if you like. I understand that from a lot of epidemiologists say that no matter how complicated the model you get and you try to make it model reality more and more accurately, it often turns out, for mysterious reasons, maybe by accident, maybe by some deeper reason we don't yet fully understand, the SIR model more or less captures what's going on anyway. So it's worth studying. So that's the idea, okay, is that you have a population that is susceptible at some initial time. Nobody is immune. Some fraction of them get infected, and the infected individuals pass on that disease to other people, and then maybe that spread is exponential, maybe it's not, maybe it damps out, and then after some time, people either recover or maybe they pass away, unfortunately. That's the model. Okay, so let's put some equations. Let's put some numbers to this. And what's about to happen over the next slide will be to write down the equations for the SIR model. And I will, as I hope to guide you through, it really is just common sense. Okay, so I hope this is something that everybody can, maybe it'll be a bit hard to follow the first time, but please go over the slides in the lecture again, because what's happening around you comes down to essentially what we're about to see in this model. So the idea is that we have a fixed population size, let's say of n individuals. Okay, so in India, n is 1.4 billion people, and that number, let's say over the course of an epidemic, let's say over the course of, I don't know, a week or two, maybe several months, we're assuming that nobody is born. So that is an approximation. But to a large extent, that's a pretty good approximation. India's population now, our population growth is quite under control. It doesn't grow more than a little over 1% a year. Um, and so on the course of a year, it's a pretty good approximation that the number of people you start out with, or the number of individuals, is the same. And so what happens is you have a population that's initially susceptible, and then some of the susceptible population becomes infected, and then some of the infected people either recover or they pass away. But if you keep track of all of those people, the number of people doesn't change. The number of individuals, whether they're alive or have passed away over the course of an epidemic, is just some fixed number. So what that's saying is that S, where S is the number of susceptible individuals, oops, plus I, where I is at any given time, the number of infected individuals, plus R, the number of removed individuals, is N, and it doesn't change. But over the course of a disease, the number of people that are in the S box, in the S category, can move to the I category, and then people from the I category can move to the R category, and so on and so forth. So there's a reshuffling of the number of people between these different categories. So because we're keeping the number of individuals fixed, we can also just divide everything by n, okay, capital N, and consider these fractions. Okay, so the S divided by n, which we denote as little s, is the fraction of individuals that are susceptible in the population. And little I will be the fraction of people that are currently infected. And little r will be r divided by n, which is the fraction of people that have been removed from the susceptible population and who are not currently infected. So that's simply saying that the fractions have to sum to be 1. Okay, so that should be pretty intuitive, I hope. And by the way, if anybody has any questions, please unmute your microphone and ask. I can't really see the chat right now, so because I'm sharing my screen. And so if anybody has typed any questions into the chat, maybe Dheeraj can unmute and ask me the question. But I'll just keep going. And I do encourage you to stop and ask, because we're about to really, we're really about to get into some very serious epidemiology, but it's all very simple. It's all, at the core, it's all very simple logic, okay? And so if the idea is that over time, some individuals can become infected, so the number of susceptible individuals can change, and some susceptible individuals can become infected, and some infected individuals can then either recover or pass away. So there's a constant shuffling away of, from here to here and from here to here, right? So SIR, okay? But the sum total has to equal 1. So if it's true that, and by sum total equals 1, meaning that the fractions have to add up to 1, that this just includes the total population, including the people who have died. So any change over time, let's call that change delta S plus delta I, the change in the fraction of infected individuals plus the change in the fraction of recovered individuals, has to equal 0. Okay, so for example, let's say you start out with the entire population that's infected, but let's say in one day, 1/10 of the population becomes infected. So after day 1, delta S is minus 0.1 and delta I is plus 0.1, and that sums to 0. And then if after 2 days, no more people have gotten infected, so delta S is minus 0.1, but half of the infected people have recovered, so it's minus 0.1 plus 0.5 plus 0.5, that is also 0. So the idea is we're simply moving individuals between these different categories. And so if we assume that in a given time step, something happens, some individuals shuffle from here to here or from here to here, then clearly over that time step, the sum of the change over that time step of these individual fractions must also sum to 0. So now we have to ask ourselves, let's think, what could these changes possibly be? Okay, so let's try and make this concrete. Let's try and make this a real model. So it's if in the case that you have the disease for some time and then you recover or you pass away, that, let's say, happens at some average rates. So if delta t is, if the amount of time is, let's say, 1 day, let's say out of 100 people on a given day, every day, one person recovers. Okay, then gamma will be one. Or sorry, gamma will be some fraction of the infected individuals. So of the infected individuals, if 1 out of 100 is recovering every day, then this gamma is 1 out of 100. Okay, so this is just saying, this is just by definition, I'm saying, I am defining that the number of recovered individuals has to proceed by some rate, but it also has to be proportional to the number of infected individuals, right? If the infected individuals is 0, then there are no people who recover by definition. So whatever this number is, it must be proportional to the number of infected individuals. And let me denote that constant of proportionality, gamma. So gamma is the rate of per unit time of recovery or death per infected person. So if the number of recovered people is increasing by this amount, then clearly the number of infected people must be decreasing by the same amount, at least. Okay? So, but there could be other contributions to the number of infected people, and that is the number of susceptible people that are becoming infected. So if I denote by beta the number of contacts an infected person has per unit time, let's say per day, that ends up infecting another person. Okay, so let's say in a given day I meet 100 people, but out of those 100 people, and let's say we model the disease in this approximation where every contact means there is some chance of transmitting the disease. So let's say out of 100 contacts, 1 out of 100 is going to result in a transmission. So if I meet 100 people every day, I am infected, I infect one other person. Okay? So that's what this number beta means. So the fraction of susceptible people must be proportional to the fraction itself of susceptible people, because if this was 0, you're not going to change the fraction of susceptible people. So it must be proportional. It must also be proportional to the fraction of infected individuals that are out there. Okay, so it's the fraction of infected individuals that who with every for every beta, this number of contacts per day, if for the number of contacts of that fraction of number of contacts, if some number beta ends up transmitting the disease, then we can say that the fraction of individuals per unit time that is now becoming infected, so therefore being removed from the susceptible population, I'm just going to write in this way. So this is an equation that you can think through in words. Okay, the number of formerly susceptible people, the number of susceptible people is going down in time as people get infected, but that must be proportional to the number of people itself. It must also be proportional to the number of infected, the fraction of infected people. So it must be proportional to I times S. Let's call it fraction proportionality, beta. So, but we know that the number of people, the fraction of people that are now going from being susceptible to being infected, this number of people that's being removed from susceptible must be added to the number of infected people. So we just add it here. And as we can see, just from thinking through this by construction, we've satisfied that the fractions remain constant over time. And this, my friends, is the SIR model. Okay? These are mathematical equations that tell you how, as a function of time, the number of susceptible individuals change, and it's proportional to this factor beta, which is proportional to the fraction of the number of contacts you have in a given day that ends up infecting somebody else. And this fraction gamma is the number of people per unit time who are infected that recover. So if you notice in this equation, this is the number of, this is how much what the fraction of infected people are changing at any given time per unit time. Let's say this unit time is per day. I see it as a common factor of I. Let me just factor it in this manner here. And immediately we notice that the left-hand side is telling us how much the fraction of infected people changes over time. Okay, and that is given by the right-hand side. So let me rewrite the right-hand side by just pulling out a factor of gamma and writing beta divided by gamma as this quantity R0. If this is a positive number, this is a positive number, this number is a positive number times a positive number minus 1. So this number can either be positive or negative or 0. So this is where some important things come in immediately. Notice that if this number is positive, this means that the number of infected people, the fraction of infected people per day is increasing. If this fraction is negative, that means if this number is negative, this means the number of infected people per day is decreasing. Okay, so the number of people per day, the infection rate per day is increasing. That's the epidemic is still unfolding. It's infecting more and more people. It's getting out of control. If it's decreasing, then we're saying that then clearly the epidemic is starting to become under control. And that critical point that separates those two situations is when the fraction of susceptible people is greater than or less than this 1 over R0. Okay? Where we've just defined this R0 in terms of the parameters of the SIR model. It's just given by these two numbers that we just deduced via hopefully something that's, I hope, is intuitive. And that has some very, very striking consequences immediately. Okay, so if we, so you realize that so this R number you may have heard in the news. When R is bigger than 1, right? That's saying that you are in general, transmitting the disease to more than one individual. If R number is less than 1, you're transmitting it less than a given individual. And so depending on the fraction of susceptible, the population that's susceptible, the epidemic may be getting worse or better. It really depends on the state of the epidemic at a given point. But what is this R number? It's just a very simplified cartoon version of reality. And in fact, because gamma is the recovery time, the number of people that recover per time, and beta is the number of contacts that you end up being infected, you realize that if the government puts in some measures, or let's say everybody starts wearing a mask, our behavior changes, this beta can be reduced. So this R0 doesn't have to be a constant itself. It could be a function of time. And this is the concept of R effective. Okay, so R effective is simply the ratio of beta over gamma at a given time, where beta is the number of contacts an infected person has per unit time, let's say per day, that results in infecting another person at that time. And gamma at that time is the rate per unit time of either recovery or death per infected person at a given time. So you see already there's a lot happening here, but in your own time, please go back to the slides and just work through the logic, and you'll see that this is now something I hope you can go and explain to your friends. Okay, now this equation, the system of equation that we just deduced from first principles, actually requires some complicated or not complicated, depending on how much mathematics you know. It requires some formalism called ordinary differential equations. What this is saying is that you have some function of time that is changing per time over time via this equation. And all of the and these are all coupled equations. So this delta S, how S changes over time depends on I and S. How I changes in time depends on I and S and gamma and so on. These are all interdependent equations. We know how to solve this. Okay, so if at some initial time, let's say at the beginning of the pandemic, we know the fraction of people that are susceptible and the fraction of people that are infected, and we know that what the recovery rate is at a given time, we can chart the course of the epidemic. Okay, so this is what SIR modeling is. Now, what I'm about to do is just show you what these equations look like when you actually go and try to solve them. Okay, so I have some links here that you can click and download little packages where you can run the simulations that I'm about to work through. We will actually, this is a very nice online simulation of an epidemic using the SIR model that we will also, I'll run through an example live with you. But first, I just wanted to go through what the solutions look like. So this, if you like, can everybody see the screen?
Yes, sir.
Yep. Yeah. Okay. So this is the solution to this equation, these equations over time, for the number of infected individuals, and if you like, the population that is susceptible. So if you imagine, so you can dial. Okay. So so on this dial, so that there is a link that you can download a little. It's not a very big file, and you download a little software. It's a demonstration package where you can run through this, but maybe you'll have more fun actually going to the next simulation. And the idea is, let's say we begin with, I don't know, 10% of our population that is infected over time. Okay, and then the recovery time takes not half a day, but let's say it takes about, let's try to model it to be COVID, let's say about a week. As of now, I set the contact number to 0. What that's saying is we begin with 10% of the population that's infected, but since they can't infect anybody, we have 90% of the population that's still susceptible, and that fraction doesn't change because I'm not allowing anybody to infect anybody. So because the infection lasts on average 15 days over a duration of time, more and more people recover, and then eventually the infection goes away. But now let's allow for people to infect each other. Okay, so I'm making the contact number bigger and bigger and bigger. So now, on average, someone gets in contact with 2, 3 people, and you see over time how the epidemic has a peak and then it decays. And the bigger the number of contacts you have, the sharper the peak. Okay, so if we, and by the way, I know this seems crazy, but there is actually a disease that you know very well that has a contact number of about 18. We'll get to it in a second. Okay, so if nobody had this disease to begin with, and in 18, and if the average recovery time is, let's say, 2 weeks, very quickly, within a week, less than a little over 10 days, 80% of the population is infected. And so if 80% of India was to turn up into a hospital, you can understand what a disaster that would be. Well, typically what happens is that there is some fraction of immunity, okay, that I'm dialing up to the disease. Let's say it's the flu. So let's say half the population has had the flu already. Okay, so then clearly, there's not that many susceptible individuals to begin with. And the flu has a contact number of about 2. Excuse me. So you see now what we have is a very gentle curve of the epidemic. Let me also make the initially infected population very, like, let's say 5%. And this idea of having, if you have a large number of contacts, the peak of the epidemic is very sudden and very high. This is not desirable. We want to instigate mechanisms to bring down the contact number, such as social distancing or curfews. And what this does is, if you've heard of it, it's called flattening the curve. Okay, this is exactly flattening the curve. So what I'm plotting here, what is being plotted here, is the solution over time of those equations that you saw before. Okay, and as you flatten the curve, as you reduce the effective number of contacts, it becomes more and more manageable. But as you increase the number of contacts, the peak becomes quicker and sharper. So there's a policy decision to be made here. Which is better? Okay, let's think about this. Now, if the disease is fatal, clearly you don't want to kill people, so this is better. But if the disease isn't fatal, then, and maybe, everybody just, takes a few days off of work and then gets back to work, then maybe this is better. You just get it out of the way quicker. The point is that this is not a discussion that exists in the realm of science alone. it has to involve policy, it has to involve sociology, it has to involve morals and ethics. Okay? So very often these decisions, these models are made by scientists and economists. And economists are some of the most, it's not that they are immoral people, but they are amoral. Okay? Economics is the study of incentives and human behavior under those incentives. And so all they care about within their framework is, questions like how productive are you? And so a lot of the decision making in different countries has been based more on economics than on ethics. And so you may have heard of some countries going for the herd immunity strategy. So apparently Sweden did this. Apparently the country I live in at the present, in the Netherlands, they did this. What they wanted to do was they wanted to infect as many people as possible so that the epidemic is over as quickly as possible so that everything gets back to normal. Turns out that was mistaken. And a country like India, at least at the beginning, it really wanted to do this. It really wanted to save as many lives as possible. I really commend the government for making that decision to begin with. Okay, but this is a bit abstract. You're just looking at a solution to an equation. So let's actually look at something a bit more visual. Okay, so if you click on this link, there's a nice simulation where you can actually simulate using this model what this would look like. Okay, so what we have here is a box. Imagine the population is a random box, and the box has people that just sort of go around, and then on average, if they come within a certain radius of each other, they contact each other and then they infect each other. And then after some time, the number of infected individuals recovers, and they become, they're no longer susceptible until they're removed. And so you can see how the dynamics of the population, the dynamics of the epidemic unfolds here. So I picked some values for it very gradual, but you saw a big peak, and then you saw a little dip, and then suddenly, it flattens out a little bit. But by messing around with these parameters, let's see, you can try different things. So let's make the infectious radius bigger, say 0.1. So the dots are more likely to come into contact with each other if they're just bouncing around. And let's increase the infectivity of the disease. So these are not quite the numbers we had in the model before, but it is indeed some combination of these numbers is going to give the beta number that I presented earlier. And we can dial up or down the number of initially infected people. So let's start with lots of infected people. We can start with not so many infected people. And let's just run the simulation and see what happens. So you see at the beginning, people get infected, and then people start recovering. Okay, and so then the susceptible population starts to go down because of it. But this is without any particular measure. So let's rerun the simulation now, but with a certain fraction of people obeying social distancing. Okay, so this is basically what it's doing, is it's making this. So this number, and this combination of these numbers is affecting that number beta, which is the number of contacts per day that will result in an infection. So if we have social distancing, you see that the disease goes much slower. Okay, and then there'll be a peak at some point. Okay, but now let me reduce the social distancing immediately. Look what happens. It goes back up again. Okay, but then of course the disease is over. So let me actually try to make this a bit more. So I invite you to go and play with this. Let me actually make social distancing quite strong, but let's just say the infection rate is also quite strong, and let's see what happens. Okay, so you see that the epidemic is peaking. Okay, but then if I relax the social distancing, it blows up. Okay, the epidemic is really blowing up, right? But then if I make it really appear again, it really flattens out the peak again. And so this is just how, and then of course, the model ends when everybody has been infected or is immune. And so some fraction of people will never actually get infected, and so they will never have caught the disease, and everybody else around them is immune. So let's just run through one more example. Let's have a larger fraction of the population infected to begin with. Okay, so there's a very gentle peak here because everyone's social distancing. Okay. And then eventually it goes away. But now let's rerun that. So let's just rerun that and just to see what the effect of social distancing is. So what this has done is it has made that beta number, the number of contacts per day that result in infection, quite small. So it's quite a shallow epidemic curve. But if I make social distancing not very um, um, widely followed, and I repeat, you see everything happens much quicker. So in the course of even like one half the time, even everything has happened and people recover. And there we go. So this is just to sort of give you a animated sense of um, what this model actually translates to. So in the end, you are solving these equations, but this very simple model. So just to summarize this model, okay? I just want to run through the logic again because it's so simple. The idea is you just have a population that at some point is susceptible, meaning that they can be infected. Maybe some fraction of them is immune, so not everybody will be susceptible. So some fraction can be infected, then they get infected. And just to recap, what that simulation was depicting was just a solution to the SIR model, which is the simplest model of epidemiology. And all it really is the realization that in an epidemic, at the beginning, some fraction of people can be infected. It could be the entire population, or it can be, maybe some fraction of the population is vaccinated, who knows? But some fraction of the population is susceptible. They can be infected. And then they get infected, and then they either recover or they pass away. So they're removed from the susceptible or infected population. And this is the SIR model. And the SIR model is simply the realization that the fraction of people who are susceptible plus infected plus removed must be 1. That's everybody. And if these fractions, if individuals can move between these different categories, the changes in these fractions must sum to 0. And if we just study how this change happens per unit time, we have that these quantities must change, these fractions must change in time according to this constraint. And we just applied some common sense. Really, that's what this model is, right? Is that at a given time, the number of people that recover or are removed from the population must be proportional to the number of infected people, right? Because if there were no infected people, no one is recovering or dying. And it must be proportional to the number of infected people, or the fraction of infected people. Let's call that fraction of proportionality, that constant of proportionality gamma. And we know that the number of people that are being removed must come from the number of people who are no longer infected. So that must come out of this fraction, must be deposited into this fraction. And then we realize that if some fraction of people if for a given person they have X number of contacts a day, but of that number of contacts, some fraction is resulting in an infection, and let's call that combined number beta. The number of people who don't have the disease that get infected must be proportional to both the fraction of susceptible people and infected people. So that constant of proportionality we call beta. And if we're removing that number from this fraction, we must be depositing it into this fraction. Okay? And studying this system of equations over time is the SIR model. And we saw it work for simulations. And let's just look at what this basic reproduction number is for different diseases. So this is some data compiled by the World Health Organization and the Center for Disease Control in the United States. And this basic R number, which is essentially can be thought of as over the course of the time in which you are infectious, how many people do you infect with the disease if you have it? So for measles, it's a lot. Okay, there's a great deal of uncertainty because this is not just some number that exists in nature. It in fact has some, depends on environmental factors such as population density, or if it's an airborne transmission, like the relative humidity. And so measles is extremely contagious. On average, every person that gets measles passes it on to 12 to 18 individuals. Okay, it's a lot of people. And same with chickenpox. The flu is somewhat less contagious, but it's still very, very contagious. On average, one person infects two to four people. So if you imagine, just being stuck in a room with 100 people, if I infect two people and then those two people go on to infect two people each, then that's four people infected. So it's an exponential process, right? Whenever the basic reproduction number is greater than one, you have an epidemic. You have an exponential runaway of the number of infected people. But because the number of people isn't infinite, right? It's a finite number of people. That exponential growth saturates until there's no longer any people to be infected with, and then they either become immune or they can get infected again. If they're immune, then the pandemic ends. If they're not immune, you have periods, you have cycles, you have waves. And this basic reproduction number for COVID-19 is, to date, not very certain. At the beginning, we thought the original variant that came from China had a reproduction rate of about 3. But it's become clear, and this is what viruses do, by the way, they evolve, they try to adapt to their host population, and it is to their advantage to become more contagious, but also less lethal, because the less you kill people, the more you have a chance of spreading, the more you have a chance of reproducing. So Ebola actually has a fairly modest reproduction number, but because it's so lethal, I think some immense fraction of people, maybe very high, at least 20% of people, maybe more, who get Ebola will die from it. It is not going to result in a very long epidemic, because the gamma fraction, the number gamma here, where the population, this factor that removes people from the infected into the removed population, which in Ebola's case is death, is very, very big. So the epidemic just doesn't spread very much. So viruses themselves have the incentive to decrease gamma but increase beta. Okay, they want to spread as much as possible, but they don't want to kill the host population as much. But the net effect of doing that is still increasing R0. Okay, because R0 is beta divided by gamma. The more you reduce this, the more you increase this, you're increasing the effective reproduction. So we are now going to arrive at, well, let me just point out what has actually happened in reality with this current pandemic in a country, which is, this data is from Denmark. And the reason I picked Denmark is that they have one of the world's most advanced genomic sequencing programs for COVID infections. They do a DNA sequence of almost a huge fraction of infected people. So they know exactly which variant is spreading at this point. And if you look, so this is the number of daily cases since the beginning of the epidemic to today. And you'll notice that Denmark had a very small wave at the time. Of course, the deaths for this wave was quite a lot. Also, there's more testing now, so there are going to be more cases. But if you focus on what the data from Denmark showed, is towards the end of the week, so around December, January, what was happening was that the original variant of COVID was actually dying out. But the reason the epidemic was still peaking was because this new variant was becoming dominant. So what an epidemic can be is actually the superposition, the addition of multiple epidemics happening one on top of another. And that's what gives this this wave structure. Okay, so what happened here was that there was the first wave, and then there was lots of social distancing and lockdown, and then over the summer, because COVID doesn't like to be transmitted outdoors so easily, and in the winter Denmark is very cold and everybody is stuck indoors. They started relaxing the restrictions, and then the disease started spreading again, and then decided, okay, it's time for another lockdown here. But in spite of the lockdown, it just got worse and worse and worse, and they had to make the lockdown even more strict because their calculations was based, the lockdown restrictions was based on an effective reproduction number that was much smaller. It was based on a reproduction number for a virus that was about 3. Suddenly, there was a virus whose reproduction number was probably around like 4.5 to 5. That was making, even with those restrictions, making the epidemic spread. So they introduced even more restrictions, and then that brought it down. And now things are somewhat under control, but it's in a country as advanced as Denmark, you see, it's not going away, even though only recently have they started opening up schools and shops. So this SIR modeling is very, very simple. It's very, very naive, but it captures some of the most important features of an epidemic. And what we're about to see now are some concepts that that I hope will make sense from just this equation. Okay, so the idea is that according to our model, the fraction of infected people per unit that is changing, the change in the fraction of infected people per unit time is proportional to the fraction of infected people times gamma, which is the recovery rate, times this combination, this beta divided by gamma. Beta is the number of contacts that result in an infection, and gamma is the fraction of infected people that recover. Let's call that number R0. And you can see just from staring at this, that if at any time the susceptible population is greater than 1 over R0, this is positive, this number is increasing. If at any given time the population is less than 1 over R0, this is negative, and the fraction is decreasing. Okay? So R0 is telling you how much, if your susceptible population is greater than or less than R0, is going to determine the course of the epidemic at any given time. But there's also something very interesting to note. Let's say there is some final steady state where infections do not increase. Okay, so we've reached some steady state of the population. And that happens when this number is exactly 0. Okay, so if this number is exactly 0, that means S is given by 1 over R0. In this state, the population consists of individuals who are either susceptible or not susceptible, and nothing is changing. There's no more infections happening. The number of infections over time is 0. It's not changing, right? So if I realize that the number of people who are not susceptible plus the number of people who are susceptible, and presume that it's at the end where there's no more infected individuals, so let's just say this is the removed plus susceptible population, this has to equal 1. So therefore, infections do not increase if I just set S equals to 1 over R and I solve for NS. There is no more infections happening when the not susceptible population is given by 1 minus the fraction of the population that is no longer susceptible is given by 1 minus 1 over R0. So if you had immunity of this fraction of the population, the epidemic is over. And this number, this threshold, is called the herd immunity threshold. And this can happen in one of two ways. One way is if enough people get infected, right? So now they're in the removed population because they've gone through this infected stage, which can be a disaster if the fatality rate is even a very small number, if the entire population is susceptible, right? So if it turns out that the infection fatality rate for COVID is 1%, 1% of India is 14 million people. And we know that, 14 million of our brothers and sisters dying is horrible. We don't want that, right? But if we can somehow vaccinate, okay, we never had to make them go through this step of being infected. If we can vaccinate 1 minus 1 over R0 fraction of the population, you have ended the epidemic, okay? And this is this magic number you may have heard before, the herd immunity threshold. And it depends on the disease. It depends on how infectious the disease is. It depends on the number of people on average you are going to infect if you get infected. So if we just calculate this number 1 minus 1 over R0 for all of these different diseases, for the different values that we have here, we see that for measles, you need to vaccinate 92 to 95% of the population. Okay. For smallpox, I'm not sure when in India. So I have a smallpox vaccination. Every Indian born up until a certain year had a smallpox vaccination, but I think they stopped because we eradicated the disease. And by the way, this you have to understand, this is one of the greatest accomplishments of humanity across the world. Every country in the world, Africa, every country in Africa, every country in Latin America, every country in Asia, we got rid of smallpox because we vaccinated everybody. So we took the number for smallpox would have been 1 minus 1 over, let's take the worst case scenario, 1 over 7. It's about 80 something, 80, 83, 86% of the population. We vaccinated 86% of the world at the time. Incredible, right? And that disease is now gone forever. Okay? But the more infectious the disease is, the more people you have to vaccinate. And because we think COVID has a basic reproduction number of anywhere between 3 and 5, or 3 and 4 actually. So realistically, I think it's going to be somewhere between 3 and 4. That corresponds to somewhere between 65 and 75% of the population. So today in India, we must have had either, so as soon as 65 to 75% of the population has either already been infected or vaccinated, the epidemic is over. Assuming that once you recovered, you no longer get COVID again. Okay? It's not entirely true for, well, it's unclear whether that's true. It's so far, it seems that indeed you have immunity. There's different types of immunity to COVID. There's antibody immunity. And so antibodies, so perhaps you're familiar with this, but perhaps you're not. So maybe I'll just spend a few minutes talking about the different types of immunity. A virus is basically some protein, some very complicated protein that attacks cells. Okay, a cell is, what our bodies are made up of. So antibodies are things that directly go and attack the virus. Okay, and so antibodies, this sort of antibody immunity is something that a lot of the vaccines are trying to give us. But this immunity wanes over time. It goes away over time, but it doesn't mean it's lost. It just means that whenever you get infected again, your body will reproduce those antibodies. Then there's another type of immunity called T cell immunity. And what that says is a T cell is another part of your immune system that when you have an infected cell, the T cell comes along and kills the cell. Okay? So it's like we have two types of soldiers in our body. One that goes and directly attacks the disease, and one that goes and directly eliminates all the infected cells, and neutralizes them so that they don't keep spreading the virus to other cells. And so it's what's probably happening is that for COVID, although antibody immunity can go away over time, T cell immunity stays for a very long time. And indeed, that's probably what we're seeing now. It's becoming clearer and clearer that reinfection is quite difficult, but it does happen for some individuals. And there's also this mystery. It's quite puzzling to me now. And I should stress, by the way, what's happening in India today has taken a lot of people by surprise. It's not that a second wave was not predicted. It was completely inevitable. Okay, I have been telling my family for the last 3 months, to not drop precautions because it's happening everywhere else in the world. So why wouldn't it happen in India? What makes India special that it wouldn't happen? That was my logic, right? Unfortunately, our government, fell victim to that mentality. They thought Indians are somehow magical, exceptional people, that we're somehow tougher, somehow we're more immune, so there will be no second wave for us. Craziness, right? And we're paying the price for it now. But what happens is, what happened in India is some people may have thought that maybe there is a native immunity, maybe that there's some cross T cell immunity in India, meaning that, and they think certainly this might be the case in Southeast Asia and in some African countries, meaning that they have had other coronaviruses that are not so bad. And by the way, coronavirus is just any virus with these spikes coming out, these spike proteins that latch onto our cells. And the common cold is a coronavirus. Many coronaviruses are completely fine. A lot of coronaviruses are lethal. People speculate that maybe people in Africa and Southeast Asia have had T cell immunity from a different coronavirus that happens to work for COVID. So that's why it's not so bad for them. So the point is that there's lots of things we still don't know, and we're learning as we go along. And this is part of how we should be thinking about drawing conclusions from our models. So I just presented a very simple model, right? And this model, by the way, is the first thing anybody learns when they learn epidemiology. Now you can imagine there are various holes in this model, right? So there are various there are various things that this model didn't take into account. For instance, the possibility that after you've recovered, you can go back to being susceptible. Okay, you can, after recovery, you're only immune for some amount of time, and then you go back to being susceptible. This is certainly the case for the flu. Okay, so if you were to work out, how this works out, just modifying this model to allow for the possibility that you become susceptible again. So you add another equation to the SIR model to allow for the rate of removed individuals to re-enter the susceptible population. Then you really start to see waves in the epidemic. There's another variation of the SIR model, which is probably actually very relevant for COVID, which is you don't immediately go from being susceptible to being infected or infectious, really, because that's really what you mean by this. In this category, that means you are actively infecting other people. You could have some period of being exposed but not being infectious. So for COVID, it's probably 2 or 3 days. You get it 2 or 3 days later, you're still going to test negative. You're not spreading it to anybody, but then you start infecting people. So, and then there is the variant, which is SEIS. So a susceptible, exposed, infectious, but then you have no immunity. You go straight back to being susceptible again. So examples of this disease are various venereal diseases, for example, they fit within this category. So these are all the different ways in which you could try to model an epidemic differently. And both the SEIS and the SIRS model, which allows for the removed population to become, or not even have a removed population in the first place, it allows for people to become reinfected. They predict seasonal recurring waves. Okay, what's happened with COVID is that these waves are because of our changing behavior and our changing restrictions. Okay, the population, susceptible population, has always been quite high, and the first wave only took a small fraction of that susceptible population and put it in the removed category, and we reduced the basic reproduction number down to 0, so we stopped the epidemic. But then that basic reproduction number raised again because we relaxed restrictions, and our behavior became a little bit more casual and complacent, and the disease started spreading again, and then we had waves. But we've also seen, yes, and whether that wave happens or not is whether the fraction of susceptible people is greater than or less than 1 over the effective reproduction rate at that given time, and that's simply a consequence of this equation. Is this factor positive? Okay, that determines whether the fraction of infectious people are going up or down over time. So we're almost at the end, but immediately I want to ask you guys to guess. Okay, so what all of these models, even these modifications, existed in the so-called compartment model. Okay, the idea is that that people are just dots in a box, and they kind of have some random chance of coming into contact with any other dots and infecting them, and so forth. So if you had to guess what is wrong or what is missing from this model, what would you guess? Can somebody tell me what they think is missing from this model? Anything, any guesses you have? Why? How could reality be more complicated?
Sir, one thing is that it is closed. I mean, new entry from outside, let's say from other border.
That's
from the
absolutely
new
yes,
and
yes. So that's
and also there might be people who are not very immune, and they are also
exactly.
infecting. So that immunity, and also there are people those who are already at
Yep.
home. So that kind of assumptions might be
Yes, yes.
wrong.
Can you think of more? I mean, there's plenty, right? So anything you can think of, right? So, well, let me ask the question: is it always true that everybody behaves the same?
No.
Exactly, right? And is it always true that everybody ends up mixing with everybody else? Right? I think you said that it's not true, right? Because some people could be at home and some people could not. So one important class of models, we're not going to explain it, that tries to modify the models to be more accurate is our so-called agent-based models. And what they do is they assign attributes to subsets of individuals. So one could imagine there are some people that travel a lot and some people that just sort of stay at home. Some people are teachers, some people are students, some people are healthcare workers, some people are old age people in a retirement home. It allows individuality to appear within this model. And of course, it becomes very, very complicated. Now, what is a problem? What is the potential problem with that? Is that you need to determine more numbers more accurately if your model is going to be any use. Because the more unknown parameters a model has, the more certainty you need to know those unknown parameters for your simulation or your understanding to reach the same level of accuracy. Otherwise, very quickly, so and this is generally true of every model. The smaller number of parameters you have, the more likely you are, however imperfectly you're trying to capture something, the more likely you are to capture it to some degree. So there's a trade-off. You can try to represent reality better and better with more complicated, more sophisticated models, but unless you know those numbers very, very well, your model is going to be useless. And this is the current situation we're finding ourselves in the current pandemic in India. Our data has become useless. It is, the number of infected individuals, it's not clear. The number of people that are dying is not become clear. I spoke to somebody in confidence who is in charge of collecting this data for, let's just call it the municipal corporation of a large city. And they explained to me how it's done. And it's very clear that in this very well-run city, they're undercounting by a factor of 3. In other cities, they're probably undercounting death by a factor of 10. And the reason is that you cannot say somebody has died of COVID unless they have a positive PCR test, even if they have all the symptoms. And so even if the doctor suspects that they've died of COVID and they put suspected COVID on their death certificate, if they even have a death certificate, the ICMR doesn't count them as death. So so we can have all of these models, but if the numbers we're inputting into this model to try and understand what might happen are inaccurate numbers, it's as good as useless. And this is the frustrating situation we find ourselves in today in trying to understand what's happening in India. I want to discuss another model of modeling epidemics. And this is something that I actually do a bit of research on, although not necessarily applied to epidemiology. This is how I know a little bit about epidemiology myself, is because there are applications to it. And it's the study of networks. So you realize that we are, as individuals, we don't live in a box where we bounce up against each other, right? Individuals have varying degrees of connectedness to other individuals or different communities, okay? So, in your household, you're very well connected to all of the people that live in the same household, right? But you're not as well connected to somebody that lives, somewhere, in a different locality, right? But there are some individuals that are extremely highly connected, right? Politicians, healthcare workers, right? Famous people, right? And so there was a very funny thing that happened, particularly in Iran, actually. So Iran was one of the countries that was hit the hardest at the beginning of the pandemic in 2020. And everybody thought that there was a cover-up. The true number of infections is definitely a cover-up, right? And the basis for that was Iranians were looking at all their politicians and famous people coming down with COVID. And they're thinking, well, if these famous people are getting it, then think about all the common people that must be getting it that they're not reporting, right? And so they misinterpreted the fact that highly connected individuals were getting infected as meaning that there was a cover-up. But in reality, what's actually happening is that the average number of contacts for a highly connected individual is much, much greater than for, let's say, an old person that lives at home, right? And so of course it's more likely that that person is going to be infected. So the study of epidemics, taking into account our social connections and how they're connected and how they change over time, is known as network epidemiology. And in an extreme case, okay, so this is just a caricature. This is a social network. These are names of, they look like Slavic names. Oh no, these are from Game of Thrones. Never mind. Yes, so these are names from Game of Thrones, if you've seen it, and it's just the connections between the different people in the Game of Thrones. Okay, but let's imagine this so I guess this is the target. I mean, it's Daenerys. I forget what house she's in, but there's a bunch of people that are very connected to each other. But imagine you live in a society where there are multiple distinct communities, but let's just caricaturize, let's just simplify it into two distinct communities. One is a very, very they like to call themselves middle class, but in fact they're extremely wealthy by Indian standards. People who live in cities, who live in, residents, who live in buildings, and then people who live in, let's just call them settlements. I mean, I hate the word slum, but this is what's used in India. And they're all very connected among each other, but there's very few connections between them. Okay? So I hope that sounds familiar to you, because that is exactly what India is. It's distinct communities that have very strong links with each other within the communities, but very weak links between the communities. And what happens in this situation, if you study the network epidemiology of this situation, is that, let's say one community gets the disease. It'll spread within the community, but it'll take some time for it to reach another community. And then once it hits that community, then it spreads within that community. So what happens is that the epidemic happens in bursts. Okay? Does that sound familiar to you? I'm not saying that this is what's happening right now in India, but I have my suspicions. And I also think that there is a degree of information bias that is occurring in the media. Every day I have friends in Europe asking me about my family. My entire family is based in Palghar district and Thane, basically. Some live in Mumbai. And they're asking me, are they okay? And I tell them, well, they live in Maharashtra. It's not great, but it's not like Delhi. What they're seeing on the news is very Delhi-centric. It is a catastrophe what's happening in Delhi. And what's making it worse is that now it's middle-class people and journalists and politicians who are dying. And so the news gets amplified. And my response is, as far as I know, the epidemic could have been just as bad in March. It's just we never heard of those people dying because they were poor. So it could be that this is what indeed could be explaining. I'm not saying it is. I'm just putting out an idea of what the SIR model may not have captured with what's happening today in India. Because we all know that India is one of these societies where we are really atomized into distinct communities. And there's a small number of individuals that interact a lot with people between the different communities, but for more, to some large approximation, some people really, really can just interact with people within their own community. And by the way, it's not just India. This is true in Israel. This is true in America as well. It just has different names. In India, there's class and caste. In America, there's whether you're white or you're black or what, humans are not particularly enlightened as a species. But anyway, this is just to emphasize that this compartmental model that I showed you earlier, this SIR model, is a simple mathematical model. And people have better models. But the problem is the better models you have, you need more numbers to determine them. So unless you know those numbers really well, your predictions become bad. And so this is a plot I just got from the Center for Disease Control website in the United States. And it's actually showing you what's happening today. Okay. So this is just a quick run through. So we'll finish very soon. This is almost my last slide. How does modeling work? Okay, how modeling works is you have a model with some parameters. So it's like a box with some dials, like a radio with some dials. And what you do is you look at past data and you fit all of your dials, you tune all of your dials such that it reproduces everything you see. So all of these models that you see here, right, have done precisely that. They've taken all the data from February to April and said, okay, our data, our model fits these points if we assume our parameters have these particular values. And then they run it into the future. Okay? And because you don't know these parameters to complete accuracy, there's still error bars with respect to some of these dots and some of these model parameters. There's going to be an uncertainty spread in the outcome of the disease. And so these are the sort of the forecasts that these different models have. And they're all very different. Some of them are, advanced SIR models. Some of them are network models. But this is the game. And so, so that's how it works, and that's where we are. So we are now in a situation in India where, if you like, the past data points for the last 2 weeks are completely horrible. They're garbage. So we have no idea what's coming. Although, from general grounds, um, we kind of have some idea. Okay, so it's just that we can't be as predictive as we like. So again, going back to how we began the lecture, the similarity with weather forecasting, you can understand completely all of the dynamics that's happening. Still doesn't mean you can make predictions, because in order to make predictions, you need to have an almost you need to have an accurate snapshot of the current state of your system. And with bad data, you can get bad predictions. And so we're left with the following epistemological question, the following really, life or death question. How do you make decisions based on incomplete information? So there's a thing called the precautionary principle, which we may or may not have the luxury to use in a life or death situation. And the precautionary principle states, unless there's overwhelming scientific consensus that a particular course of action is not going to result in more harm, don't do it. Okay? So by precautionary principle, we should not be using GMO crops. Okay? We should not be using genetically modified crops. However, not every society has that benefit, because the population of Africa is exploding, and there will be food insecurity unless they switch to genetically modified crops. So it's not just a scientific decision, it's an ethical and a moral decision as well. And every society has to decide for themselves what the appropriate choices are. But an important factor in that decision is you have to understand the asymmetry of risk factors. Okay? If there is a course of action that has very little downside, but potentially huge upside, even if you're not sure of that upside, for example, wearing a mask, right? Then just do it. It doesn't hurt to do it. Nobody is harmed from wearing a mask unless you have a serious respiratory disease. But that fraction of people is very, very small. So even at the beginning of the pandemic, when people were still arguing whether COVID is spread via close contact or by touching things, it's called fomic transmission, or airborne, they weren't sure. Some people were like, shut up, who cares? It doesn't hurt to wear a mask. And so they wore masks, and turns out that it was true. So please wear your masks. It really helps cut down the effective transmission rate. But there are some people, some idiots in America, for instance, and in Europe, the country I live in, that are just like, no, you're taking away my freedom. I'm not wearing a mask. Disaster, okay? The point is that whenever you have a decision based on incomplete information, if something doesn't hurt, then do it, okay? But or don't do it, as the case be. But you have to decide for yourself what that is, right? And so another example that's actually closer to a scientific argument I myself personally had with people, which is the use of of vaccines before they've gone through all the tests. So when the government of India released Covaxin, okay, which is a very specific type of vaccine, it is an inactivated virus vaccine. What they did was they took coronavirus, they took away its infected components, and they're injecting that into somebody. This has been practiced for at least decades, if not a century. It is safe. It is completely side effect free, right? I mean, it is the safest form of side effect vaccine you could have. So, but there are other types of vaccines, like these mRNA RNA vaccines, the Moderna, the Pfizer vaccines, that are extremely untested technology. And there's another type of vaccine, these live activated viruses. They basically inject live virus. It's an actually infectable virus, but it's not going to kill you, which is what Covishield, the AstraZeneca virus is. So there you really do have to test and make sure that it doesn't have any ill side effects. And in fact, in Europe, they're now removing Covishield or AstraZeneca, as they call it here, because it's causing blood clots in young people. But the rate at which they're causing blood clots is so minor that I think it's crazy that they're stopping it. But the point is that there's another factor here, and my argument is that there is an asymmetry of risk for Covaxin. My own mother is immunocompromised, okay, and I told her if she has a shot to get Covaxin, please take it, because there is very little possibility of harm and only benefit. And if it turns out that Covaxin is not a very effective vaccine, who cares? There's very little harm from taking it, but the upside of not getting coronavirus is huge. Okay? So every risk factor has an asymmetry. I'm not, by the way, I'm not telling you what to do. I'm not telling you how to think. I'm pointing out to you in ways in which to organize your thinking here. And everybody is flying blind. Every government in the world is flying blind. They don't know the storm that they're flying into. They're making decisions and they're learning on the job. And so I wanted to end with a video from World Health Organization official on precisely this type of thinking at the beginning of the COVID pandemic. And here's what he had to say about everything.
Sir, not audible.
Sorry, can you hear the audio?
No, sir.
Oh, there's no
No,
audio.
sir, it's not audible. Only
Oh, I'm sorry.
visuals.
Oh, I'm sorry. Okay, well, please watch this video in your own time. The speaker is saying essentially that at the beginning of an epidemic where you don't know what's actually happening, you have to react quickly. And even in imperfect information, even when you don't know, if you wait around for perfect information, the virus will get you. You have to act quickly, and you have to act fast, and you have to act at the community level, and you have to act decisively. And it's a very relevant quote to what's happened to us. We have brought it on ourselves. The way you can debate any, you can debate, the human toll of the lockdown that for the first time we did it, it was horrible. But it was decisive action and it saved lives. And all that hard work, all of those people that sacrificed their livelihoods has been thrown out the window with this second wave. Yeah, I am furious. I'm very angry because so many people suffered to bring this epidemic under control, and then simply because of our own complacence, because of our own sense of that exceptionalism, that we're special somehow, that we're not going to have a second wave, we relaxed. And what really bothers me is that there were field hospitals that were being dismantled. There were mobile isolation wards on trains that were dismantled. There was oxygen surpluses that we started exporting to certain countries that we were lazy about vaccination, right? I mean, a country that produces 2 billion vaccines a year should have been able to vaccinate everybody in a matter of months. We didn't do it, okay? And so, this is the most frustrating thing for me, is that we did the hard work. We did the hardest thing possible, and the poorest people in our country paid the price for it. Okay, and we threw it all away. And so I'm really upset, but it's not lost. I think there is a way out of this, and I think now people have taken it upon themselves. They're not relying on the government, and it's definitely going to get worse before it gets better. But most of the deaths that we're seeing right now is because of lack of oxygen. It's as simple as that. 90% of the people that you're seeing on TV in Delhi and all these places that are dying could have been saved with just 5 hours to a few days of oxygen. We could have saved them, which isn't to say that a lot of people aren't going to die even with oxygen. Of course they are. This is a very bad situation, but it didn't need to be this bad. But anyway, I just wanted to, that it was a topical thing. I wanted to share with you this introduction to the science of epidemiology, not to help just for me personally, whenever something bad happens, I could sit around, I could get upset, or I can read a lot and I can analyze, and that's kind of just my personality type. And it was my way of sort of helping process what's been happening and sharing it with you. But um, I hope you've understood a little bit about the science behind epidemiology and why forecasting is hard. It's like the weather, and what we can basically say is, in a nutshell, there were lots of people saying there's a storm coming, and they were saying this since February. I've personally been telling my family that there's a storm going to come. I didn't know when it was going to come, but my mother is immunocompromised, as I said, and so we have been sheltering her as much as we can. And I told them not to relax, and I'm very happy they listened to me, my parents. Um, but many of my relatives didn't, and many of my relatives have fallen ill. But thankfully, they've recovered. But um, the just like weather forecasting, like a lot of people were pointing out that a storm was coming, and then the government was asleep. It was asleep, and so here we are. So we're in the middle of the storm now, and what we're now doing is, I think if we can scale up oxygen production, we can bring down the deaths quite a lot. But we're now also going to have to deal with another economic catastrophe that's going to obviously disproportionately affect people in the lower sections of society. And this is economically lower sections of society. And this is a complete man-made disaster, really. So anyway, so I'll stop my presentation. We can just chat about it now. I have time for some questions or comments. Um, yeah, so that was the basic introduction to um, epidemiology. So I'll put the slides up. And by the way, if you're interested in maybe a bit of in the next module where we're going to, so like I think Ramiz has mentioned before, after the next lecture on election polling, where we're going to really get into the sampling and sampling variants and how to make samples. We'll take a pause. We'll have a little coding academy, and then maybe we can design even a data science module um, for pandemic modeling in the application. So in the next more advanced module that we're preparing for the next step in this school. So yeah, so that's a presentation. So if you have any questions or comments, please just unmute and ask or let me know.
Thank you, sir. It was very wonderful lecture today. So my question is, sir, we in news we are the news is coming that in Delhi there is a test positivity rate of around 30% in Delhi.
Yep.
I don't know about other parts of the country, but if let's say if it is 30% nationwide, so what does that mean? I mean, would that be uh, I mean, how lethal would that be in terms of death?
Okay. So there's some good news and some bad
And
news. Okay. So
how
the
long
good news.
will be this going on? I mean, peak, is there going to be peak anytime near soon, or what
Yeah.
is?
Yeah. Okay. So there's many aspects to your question. So the good news is, aside from Kolkata, um, test positivity ratios are much lower everywhere else in the country. Now, so even though we're not testing enough, the test positivity ratio is still it's a less biased estimator, if you want to use the language of our previous lectures. In Mumbai, it's about 24% now. But the thing is, during the first wave, it was also 24%. It's actually less, a little bit less. So Mumbai was always under testing. And there, the situation was relatively under control. The point is that with adequate healthcare, adequate planning of medical facilities, it needn't be so bad. And in a country as young as India, this many people don't need to be dying. Now, the shocking thing to me is this government, and the stupid, way they planned that election in West Bengal is murder. They
Sir,
have
sir,
now.
sir, sorry to interrupt. So there
Yes.
is one thing that
Yeah.
I mean, journalists in their reports are saying there could be, I mean, deaths could be in multiple of 10 times, even maybe more than that. In on crematorium, there are government data is reporting only 3 deaths, and actually there are around 300 deaths. So these kind of data are not reported. So those pandemic, those who are studying this,
Yeah.
are they reporting official data, or what? How they are making decision? Inaccuracy
Yeah.
is in itself in government data. So how
Yeah.
can
Yeah.
we make accurate
So the thing
decision?
is, you have to separate between real-time data and what the eventual official statistics will be. So what happens is there's two things that happen. One thing is that the death is not ever going to be recorded as a COVID death if the person doesn't get a PCR test before they die. And what we're seeing right now is people are dying before they're getting PCR tests. So those deaths will never be counted. Now, even those deaths that are confirmed COVID deaths, there is an actual bureaucratic process that involves coordination between the municipality and the state and the ICMR that takes some time. And some states are better than others at it. And so I think Maharashtra is probably one of the more accurate test places. And even then, I would say in the end, they will undercount between 3 to 5. You should also understand that if you look at crematoriums, and this is something that I actually sat down and did a few calculations myself. Okay, so somebody said in where was it in oh yeah, in Indore, there was something like 400 and something, no, 1,000 cremations, excuse me. Yeah, 1,000 cremations over 14 days, right? And the official statistics only said something like 43. Now you understand that in India, 7 people die per 1,000 individuals per year. Okay, so in that same time period in Indore, half of those 1,000 people are dying from natural causes anyway. Okay, so the problem is for those of us who've been to a Hindu cremation or a Buddhist cremation, you know that it takes time. It takes 6 hours for a body to be really cremated. So it's going to it's there's a if you like a cognitive bias that appears from the visuals that it looks worse than it is. It does look worse than it is. Of course, it's bad. I'm not saying it's not bad. It's bad, but it's not as bad as it looks. So let's take this example for Indore, right? So in these crematoria, they said 1,000, but only 43 official COVID deaths. Okay, but so they're saying 20 factor 20 underreporting. But hang on, half of those deaths are natural. Okay, and of that, I would say some fraction of the remaining factor 10 underreporting is just a backlog, a bureaucratic backlog. And then once the ISO, you see, because finding that ICO, so the way it works is that you get it's anonymous, so you get a number, and the state, the city has to tabulate that number with the ICMR, and the records are in different places. So I know for a fact that in some places, like in Mumbai, they're very, very strict about it. In some places, it takes a bit longer, and so in the end, what's going to happen is that deaths will be undercounted by anywhere between 3 to 5. I mean, 3 is a lot even in Mumbai, but definitely somewhere between two to three in like the major metros, and in the rural areas, maybe between 3 to 5 to 6. But 10 is a crazy overestimate, and I think people are just being dramatic, and I don't blame them because the visuals we're seeing are horrible. But at times like this, you got to tune out your emotions. You got to be clear. You got to think. And one of the things that I want to point out is, Indians we are by nature very narcissistic people. We love to think about ourselves. And I know that this is bad, and I hate to sound like I'm cold when I say this. This is horrible what's happening to our country. But still, even if this epidemic rips through the population, like it looks like it's going to, if we can get our oxygen supply situation in order, and by the way, every southern state has an oxygen surplus. Odisha has an oxygen surplus. If we can figure out how to transport the oxygen from one place to another efficiently, many people don't need to die. And in the end, our final death rate, including undercounting, I think will be much less than some poor countries, not poor, but like countries like Brazil. Brazil has been completely shattered. Okay, what we are going through is now we are experiencing what other countries in the world have been through. If you follow the news in other countries, Bolivia, and I mean they're and it's always poor people that are dying. Okay, so my own analysis is that I don't think what we are going through is particularly bad. I'm sorry to say that. I think what we're going through is particularly man-made, and I'm really angry about it because in our country we're the world's largest producer of vaccines. We're the world's largest producer of medical supplies and medicines. One of the world's largest producers of oxygen. Why is this happening in our country? It's happening because our politicians are idiots, okay, and they aren't listening to people that were telling them what to do. And in fact, what is happening is that they're clearly realizing that there's no consequences to their actions. And I'm sorry, I'm getting a bit upset here. I shouldn't, but if your question is yes, how do we interpret what's going on? At this point, what I would tell you is that all of these reports you're hearing about factor 10, factor 20, you can forget it. It's not that high. The underreporting is high, but it's going to be somewhere between 5 and 6, which is still a lot, by the way. That's a lot, but not 10, not 20. And this, what we're seeing is a time lag, okay? And also what you're seeing is crematory. There's a visual effect, right? You have to understand there are cognitive biases, right? So then we all have brains that are subject to different cognitive biases. And one of them, the most famous cognitive bias is well, let's all get into it. The point is that the crematoria that you're seeing are close to hospitals, okay, or they're designated crematoria for people to, so at certain crematoria, the visuals are going to be very, very bad, and there's going to be a big counting. But just remember that on top of all the people dying of COVID, at any point, there are still Indians dying from natural causes, and it's a lot of people. Okay, so in the statistics I looked into, in Indore, I calculated that over 13 days, something like 400 something people are going to die from natural causes anyway. Out of the 1,000 people that were cremated, or actually something like 600, I forget the exact numbers, but it was a significant fraction, such that the person's estimate of factor 20, 30 goes down to about 10. And of that factor 10, it'll go down to about 5 once the official record catches up with the, with the local records. So, indeed, but looking ahead to the future course of the epidemic, if West Bengal, so West Bengal is headed for a very catastrophic situation, and it is completely because of this election that the BJP basically rigged to get the election commission to arrange it over so many phases, and you can just see the number of infections go up with every stage of the poll, and it's bad. It's going to get bad there. I think every state in India, every locality has its own individual epidemic. And in Mumbai, I think it's already on its way down. I think in Tamil Nadu, it's also on its way down. So the good news is, wherever you are, if you are in the middle of it, if the experience of Mumbai and Pune and Chennai is anything to go by, the worst of it will be over in a couple of weeks. Okay, but this still doesn't mean it's not going. And the worst will be over in a couple of weeks if everybody takes appropriate action at this time. But that doesn't mean it's not a disaster. So my short story is this is bad, but it's we should keep it in proportion. I think in the end, lots of things will be broken, lots of lives will be gone. But India is a big country, and also remember that Indians are very socially connected people. Okay, on average, an Indian person knows many, many more people than, let's say, an average person in the West. So you are going to know many people who get affected. Whereas in a country like, I don't know, the UK, people just take the size of a wedding as a rough indicator of the size of someone's social network. Indians are factor 5 times more connected than people in the West. And so there is a bias, there's a cognitive bias that it seems worse for us than, let's just take my own family, for example, on a normal time, just every week I call my parents, some years, every other week I hear of a family member passing away because my family, we're spread out, there's lots of people, right? But if I talk to someone in the West, they, maybe they have a death in their family once every 2 years, right? Does that mean Indians are dying more? Maybe it's a bit true, but really what's happening is that there's just more people in your social network. So it seems worse to you psychologically. Yeah, there's a psychology of big numbers at play with what's happening here. And everything looks worse on TV because they're incentivized to make it look bad. In the final analysis, this will be a bad epidemic, but compared to other countries, we will be among the average. Unfortunately, India is just so big, it's a lot of people. And there's way too many people that needed to die, considering that it didn't have to be that way.
Okay, sir. Thank you.
So I have to run now in a few minutes for another meeting. So let's conclude. I only meant to go until 4, but I'm sorry I took up more of your time. But if you have any questions about the material that was covered, so this is, by the way, this is nothing. Of course, it hits a lot on some of the concepts we covered in our courses. It's really just an independent, if almost, I hope, like a more advanced version of a TED Talk for you to see a little bit about how all of this is done, and for you to understand why it's so hard. It's as hard as predicting the weather, even if you have perfect data. But even if it's hard to predict, you can still have a firm understanding of what's happening. So if you like more references or more discussion or more articles, just please put it in the stream and on the Google Classroom, and I'll be happy to answer questions. Okay, so have a good evening, everybody, and take care of yourselves and take care of your loved ones. And I will see you on Monday. Jai Bhim.